Now let's go back to the problem. There is one thing very good about it because in this problem, in this experiment, the sample sizes are the same. So we get to calculate the same number for one, no matter what pair, what pair, which pair of all possible pairing, all possible pairs, this number will always be the same. So it's actually calculating the difference between two means, whether the means are whether the means is greater than 6.8. If it's indeed greater than 6.8, then we say that there is a significant difference. Okay, let's move down to a table right here. Let's arrange them to be in an increasing order. 29 smallest, 30.5 the second. The third one is 42, and the last one. Remember, these are the mean battery lives in hours. Mean battery lives in hours. We want to find the best. Of course, everybody has eyes. I know that this is the highest, but however, are you sure that there is significant difference? Are you sure? Well, this is for us to decide because we are statistician. So there is an important question to ask whether the difference is significant. If the difference is significant, then we get to conclude that this one alone is the best. If the difference is not significant, then we get to conclude that the two share the first place. And oh, yeah, okay, there is another one, 30.5. So it's our job to say, to conclude, to be able to conclude that whether the difference is significant. Okay? It is not such a difficult work because we calculated the minimum significant difference is 6.8, right? 6.8. And it is easy to see that the difference is 1.5. It's not so large as 6.8. So the difference is insignificant. And also the same 1.5 is insignificant. But however, these two. Okay, that's not such a terrible work. You know, let's find it is a sound operation. Yeah, we find the minimum significant difference, and we order them from the smallest to the largest, and calculate the difference of adjacent means, and compare with the common minimum significant difference, and which is 6.8. The comparison is easy. So these two are not significantly different. So are these two. But however, the gap between the two groups is significant. So we know that from 6.8, if we use 6.8 for the minimum significant difference, we have the result. The two share the first place because we recognize, we acknowledge, we accept that the difference 1.5 between the two is not significant. So they are not significantly different. Okay, however, we can use them because they are significantly inferior. Okay, now the conclusion. What seems the problem? What seems to be the problem? Okay, what seems to be the problem? This is a much bigger problem, but however, the original framework, you have done it. You have I lead you through the derivation, the development of the conclusion, so you know a little bit. But however, let us go back and let me ask you some basic questions. What do you need? What do you need to make the final conclusion that these two are the best and no one else? These two are to be used. Okay, these two have the same uh, the the same longest average lifetime. Okay, the final conclusion. Don't forget you are using statistical inference. You compare these two. You compare these two. You compare these two. Actually, you did comparison 3 times, right? 3 times. Are the comparisons 100% precise? Are you sure that the result is 100% correct? Yeah, I got you. Of course it's not. We're using statistical inference. We're using statistical statistics, testing hypothesis, right? We're using statistical concepts. So there will be a rate of error. There is a percentage of making a mistake. And ordinarily, without further mentioning, we're ordinarily using alpha equals 0.05. So the result is subject to an error rate of 0.05, right? And the same thing when we compare these two. And same thing when we compare these two. So actually, the conclusion is subject to an error rate. The error rate is in an accumulation of the 3 comparisons, right? How are they accumulated? How are they accumulated? 0.05 plus 0.05 plus 0.05? No, not necessarily. That is part of the difficulty. We don't know how it is accumulated. But anyway, one thing is for sure. The final conclusion based on the 3 guesses, which are not, none of them are 100% precise, is due to an error. Okay, is due to an error rate, and the error rate will be definitely larger than alpha. Okay, so the final conclusion is shaky. We don't have enough confidence in it simply because it is based on multiple comparisons, statistical comparisons. Okay, did I have your attention? Are you convinced? Are you persuaded? Well, anyway, I'm letting you know that this problem is serious. How is it going to be resolved? The first thing that people can ever think of is to make the error rate for each comparison smaller to achieve a final error rate of 0.05 as regularly required. Yeah, that's normal. And okay, let's do that. And the first direct result is the development of Bamperoni. Okay, Bamperoni. Wait a minute, where's Bamperoni? Bamperoni used a quick and dirty way to make the alpha smaller. Okay, alpha divided by 2m. Originally, there is a name, okay? There is a name. Suppose we use alpha equals 0.05. Originally, without any declaration, without any alteration, the original critical value is the margin of error we have seen back there, and it is called Fisher's LSD. Fisher's LSD. Nothing is changed, okay? And the second one is Bamperoni. Bamperoni is quick and dirty. We want to make alpha smaller. We divide the whole thing by m. What is m? M is the total number of pairwise comparison necessary. There are four. There are four. Wait a minute. There are four treatments. Four choose two. It is 6. So M is 6. M is 6. Let me show you where it is. Okay. M is 6. The degrees of freedom is 20. And alpha M is 1. When M is 1, nothing is done. Nothing is done. Nothing is different. So we're using Fisher. The percentile is 2.084. And when M is 6, 2.927. 2.927. So 2.927 multiply the same thing, the standard error. Okay, and there is a third method. It is under the name Tukey's HSD. The critical value is calculated differently. We're using a table. The table is called studentized. Yeah, the table is right there. This is critical value, and this is the value. This is the table that we use. Remember what we use? This degrees of freedom is 20. 20. Okay, and here the number of means. For this problem, number of means is 4. Now remember the third column: first, second, the third. Okay. 20. 1, 2, 3. 3.96. 3.96 for 0.05. For 0.01, it will be something else. For 0.05, 3.96. Now remember, this table is not in the book, but however, it's on the internet everywhere, so you get to find it. Well, you don't have to worry about it. 3.96. 3.96. The other things are there, and this number, this denominator, is the common sample size. Oh yeah, okay. One thing to remind you, Tukey works for equal sample size case. Equal sample size cases. Okay, equal sample size cases. And it's always so that Fisher is the smallest. Tukey comes between, and the Bamperoni is the highest. Okay, of course, we know that these are confusing. The exact purpose of finding these are really not so clear. But however, for beginners, the example usually are so selected. The examples are selected so that the young minds are not confused. So probably using everything, the result will be the same. And you know, the confusing cases are that using different critical value, using different minimum significant difference, you get different result, and the result will be confusing otherwise, and you will ask, what should I do? Well, it's a big question. I'll answer that question later. Let's take a break.